This is core concepts, or core component, mock exam, and it's mock exam number 2, and we're up to question 3. Oh, it's happened. It's happened. You just like your teacher said, at some point you might have to draw a graph on an exam, and here it is. Oh dear. Right. Here we have a table of data, and it's the activity of an enzyme. So this is an enzyme question. So immediately I'm thinking at some point we might have to mention active site, substrate, product, enzyme substrate complex, that sort of thing. And pH, I'm already thinking pH, the effect of pH on enzymes and optimum pH, what happens either side of the optimum, and a rate recorded as proportion of maximum activity. Okay. Construct a graph. Great. So, drawing the plots with a smooth curve. But didn't we just say dot to dot in biology? Right. We need our... If we draw a graph, then... Draw a graph, I'll just sketch over here. The graph is going to look like that. This is our x-axis, that's our y-axis. On our x we're going to have the independent variable. On the y we're going to have our dependent variable. And what are we specifying? What am I changing in this? It's the pH, so you're going to be at the pH at the bottom. And the dependent variable. The dependent variable depends on the experiment. We don't know it at the start. We're measuring it, so that's going to be salivary amylase up the side. So I'm going to put the pH at the bottom and the rate of reaction. Rate of reaction proportion maximum activity. So I've just copied that out, then I can't get it wrong. Yeah, if I change it in some way, it might change the meaning. And I'm going to write salivary amylase. Well, that's going to be one of our line that's plotted. Okay. Construct a graph. We've got to go from 1 to 13. From 1 to 13. Do these squares tally up with any measurements? Dear me. No. And there's not even any big lines on it, so this is quite a tricky graph to draw. What would happen if, so we're down to trial and error, what would happen if I used, say, 10 squares for each pH? So 10, 20, that's, we're not going to fit that on our graph. What about 5? So if I had 1, 2, 3, 4, 5, so that would be pH 1, 1, 2, 3, 4, 5, pH 2, 1, 2, 3, 4, 5, pH 3, 1, 2, 3, 4, 5, pH 4. You can see that we're going to use more than half of our scale, so that's what we want. So 0, 1, 2, 3, 4. But hang on, you say we haven't actually got a pH 2, so why am I putting a pH 2 on there? Well, this scale has got to be linear and at regular intervals, or else when we join the points, it's not going to be representative. So this has got to be in regular intervals. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. So that scale there uses more than half of our graph paper and going in that direction. And going up the side, again, this is proportional inevitable percentage on there as our units there. pH doesn't have any units. What's our maximum number needed? 100%. So 100%. How many squares have we got? We've got 100 squares. Could it be 1 square is 1%? No, there's not 100 squares there. You know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If that's 10, if I times that by 10, I don't think we're going to have enough. So I'm going to use 2 squares for, so 2% for 1 square. So I'm going to essentially use the same scale. So 1, 2, 3, 4, 5, and I'm going to use that as my 10%. And keep going. 1, 2, 3, 4, 5, 20, 1, 2, 3, 4, 5, 30, 1, 2, 3, 4, 5, 40, 1, 2, 3, 4, 5, 50. It's 5 marks for this. So you can sort of imagine where the marks are going to go. It's a lot of effort for 5 marks. Certainly when later on you're getting 2 marks and 1 mark there for saying something pretty straightforward. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. There we go. So it's moving half of that scale as well, more than half that scale. I'm drawing this in red just to make it stand out. You would draw this in pencil. The number of mistakes you're likely to make, particularly when it's asking you to join the plots of the smooth curve. So if you've got a pencil and a rubber, that's definitely the best way of doing it. Let's plot our points. So at pH 1, it's 0. So I'm just going to use a cross. So you could use a dot with a circle around it, or a cross. I'm going to use crosses because that's the way I've always done it. pH 3 is 0%. pH 4 is 2%. So each one of my squares is 2, so that's going to be on there. Now, pH 5 is 12%. So up to our 10. And this is really difficult without our occasional bold lines on. pH 7 is 100%. Whee. That is really difficult to keep an eye on that line. Yep. pH 8 is 40%. So that's the line there and there. pH 9 is 8%. pH 11 is 1%, so that's half a square. And pH 13 is down to 0. So normally, drawing a graph, if it didn't say join the plots with the smooth curve, I would just put my ruler on and join dot to dot. Today it's asked me to do something slightly different, and that's probably because this is actually going to be a curve. It's not, this peak here is going to be slightly more rounded, and sometimes you just need to so good so far. This could go horribly wrong. Trying to trying to go through the points, that one, so go down to 0. That's not bad, not bad. Line there. It's not a million miles away from where it should be. So that is our graph. Let's see where the points are awarded for. So the points are awarded for a linear scale. So a regular linear scale up with those, and good use of paper, over 50%. So 1 mark for our scales. We've got pH along the X and percentage up the Y, and we've got labels and we've got percentage written, so that's the 2nd mark. There's 2 marks for correct plotting, so the examiner will check these crosses and they'll take off the mark if I've done 1 wrong, and they'll take 2 marks off if I've done 2 wrong. So there's 2 marks for the plotting and a smooth line for this curve. So I think we might have 5 there. The stomach contents are pH 2. Use your graph to determine the activity of salivary amylase in the stomach. So this is a typical thing for a graph. They give you a new number and ask you to use the graph to find the other one. So hang on, 2's there, 1 0 and 3 0. So most probably 2 is also going to be 0. We don't even need to measure that. So 0, and that's our percent, or no activity. On your graph, draw a curve to indicate the probable pattern of activity in of the stomach enzyme pepsin. So this line here is, what was that? That was salivary amylase. So salivary amylase and pepsin. So we need to decide where the maximum activity is going to be, and where, would it be a big wide peak, or would it be a narrow peak? It's going to look fairly similar to this, but it's in the stomach, and it tells you it's in the stomach, and the stomach contents are pH 2. So one thing I'm going to be pretty sure about is that for 2, that's going to be our maximum activity. And then probably fairly a narrow peak, because the stomach's at pH 2, and it's not going to vary very much. So we're looking for fairly sort of narrow peak. That's it, not brilliant, but that sort of thing there. And we're going to label a curve for pepsin. So probably a little bit too fat at the top, who knows. And the marks there are indeed the peak at 2, and they'll give you a little bit of leeway, half a pH or so, but really it told you it was 2, so you should have put 2 on your graph. And for it, again, having a narrow range, certainly less than 5, so I think we're okay there. Explain how pH can affect the activity in an enzyme. Right, thank goodness we're away from that now, and we're just going into straight normal biology that you've learnt. So here we go. And right at the beginning, as soon as we saw pH in enzymes, we knew we were going to talk about active sites and things like that. So here we go. So pH can affect the shape of the active site. Now, extreme changes in pH will denature, there's another key word there, denature the enzyme. So shape of the active site, denaturing the enzyme, using all the correct terminology. Why? Because changes in pH alter the bonds, and if we go back to our first question, well, these bonds that rely on pluses and minuses, aren't this ionic bond here, then that's going to be affected by our pH, because our pH, what is an acid? An acid is a proton donor, so it's giving us pluses, is this acid. So and if we change the concentration of pluses, that's going to affect our ionic bonding. So that's the one I'm going to go for. So changes will alter the ionic bonding, and I'm going to put where they are in the, for example, tertiary structure, because it's a tertiary structure that makes this the shape of the active site. And we could also, we got our 3 marks there, so that's our bog standard answer. We said affects the shape of the active site, denaturing the enzyme, and we've explained about the ionic bonding and tertiary structure. But we could explain, that's why it's going to denature, but why does it go down a bit on either side? You know, we could say, well, it just lowers the activity with a small change, so some of these are kind of reversible. So if only a small change, then this just lowers the activity. But we've already got our 3 marks there. During the investigation, described above, state 2 factors that kept constant. These are our controlled variables. So again, we put a lot of effort into this graph to get 5 marks. Stating 2 controlled variables for 2 marks should be fairly straightforward. So in the enzyme, what would we keep the same to make sure we're only testing the pH? Well, you should be thinking about other things that affect enzymes. For example, if we did our salivary amylase at 30 degrees and then on the next day we did our peptin experiment and it was only 20 degrees, well that could have had an effect. So things like temperature. So temperature of the mixture temperature of the enzyme, and also the concentrations. If you've got a higher concentration of one of these than the other, then of course it's going to be different. So enzyme concentration and also the substrate concentration. Then, if one's got more substrate than the other, then it will give a slightly higher reading. So enzyme concentration, and we could have here, so you've got your 2 marks there, but we could have substrate concentration. Even though I'm writing it fairly scruffily, don't put conc, put concentration. Don't put temp, put temperature. Always spell these words out. And we could have time for the whatever's going on in the experiment. It doesn't tell us, so we're going to be kind of slightly making things up there. But go for these nice obvious ones. Part E, what would be used to control the pH? You should have used these in class, and these are just called buffers. They're just little little tablets that you dissolve in water, and then that gives us our pH, and it will keep the pH at whatever it says in the tablet. So you just need to know that word. So 40 marks, pretty tough drawing the graph unless you've done practice and done our graph math skills. But the second half of this is pretty standard theory, so you should have certainly got those 40 marks.